Hi, in this video, we want to go over some introductory concepts and terminology in statistics using R. All right, so here we just want to touch on the big ideas, some things that we need to know about if we're going to be talking with other people about statistics. Many of these concepts are really more intuitive, and we're just putting labels to these ideas so that when we communicate with each other, we can speak clearly. All right, so statistics is a branch of mathematics that deals with the collection, analysis, interpretation, presentation, and organization of data, right? I mean, that's what it is. And so let's go into a few basic concepts. First one is going to be data. All right, so data refers to the information that is collected or observed. So these are our measurements that we have to work with as we run our analysis. So it can be like numbers, words, images, anything that you can consider an observation or a measurement is potentially data. Data can be further classified into two types, and this is the classic classification when you think about data in a more traditional aspect. Things like videos and texts and recordings and things like that are kind of a little bit outside of this lane. Here we're just talking about like the classical point of view, just as a framework to start from. So we've got qualitative data and quantitative data. All right, so qualitative data is non-numeric and cannot be measured using numeric techniques. All right, so examples of this are color, gender, and marital status. Right, so these are values that we really can't assign a number to. It doesn't make sense to add genders together. It doesn't make sense to subtract marital status. All right. Now, quantitative data is numeric data, and we can apply numerical techniques to our data. So some examples of quantitative data are height, weight, and age. So height, it makes sense to add 1 to a height. So if we're talking about inches, adding 1 means a person grew. Weight, subtracting 5, they lost 5 pounds. And so numerical operations make sense with numerical data. Now, so here's something to think about. What about something like Social Security numbers? Does it make sense to add Social Security numbers? No, it doesn't. All right, so even though it's a number, that's actually qualitative data because mathematical operations don't make sense with ID variables. All right, so here are some examples. And so let's create a data set in R that has qualitative and quantitative data. So we're going to call this student data, and we're going to have 3 variables: name, gender, and age. So here, name is going to be identifying the subject of the data set. Gender is a qualitative field for that person, and then age is a quantitative field for the person. All right, and now to be able to build a data set, this is how I can manually build a data set in R. I'm going to use the data.frame function. So here is where it opens, here's where it closes. This arrow here says that I'm assigning student data to be the data frame that I produce over here. All right, so now when I use the data.frame function, I'm going to name the column of data that I have, name the data field, and then here is a vector of the names that I want to correspond to the name column. Here are the gender values. So here's gender. This is saying that I want the column to be in the data frame to be called gender. And then here are the values I want to have. And then the age column of data will be 18, 19, 17, 18, 20. All right. So now let's just take a look at our data set, and we can see that this is how it works out. Notice that the names of the data fields don't have a numbers. This 1, 2, 3, 4, 5 indicates the row number inside R. All right, the next thing to talk about are variables. So a variable is a characteristic or attribute that can be measured or observed. Variables can be further classified into 2 types. We have an independent variable and a dependent variable. An independent variable is a variable that can be manipulated or controlled by the researcher in a study, is often denoted by X, and is the cause of change in the dependent variable. All right, so here, independent variable is a variable that is not influenced by the dependent variable, while the dependent variable is influenced by the independent variable. Dependent variable is a variable that is affected by changes in the independent variable, is often denoted by Y, and is the outcome or response to changes in the independent variable. So a good example of this is going to be temperature in terms of weather temperature, and ice cream sales. All right, so if it gets hotter, we're going to probably see ice cream sales go up. If it's colder, we would expect ice cream sales to go down. But if ice cream sales goes up, that doesn't necessarily mean the temperature is going up, right? The temperature is going to do what the temperature is going to do, regardless of what's happening with ice cream sales. Around Christmas, we're going to be having pies at Thanksgiving and at Christmas. And so there's probably going to be an increase in ice cream sales, but that doesn't mean we're going to have an increase in temperature. So the independent variable is temperature because it's not influenced by the dependent variable, and the dependent variable is influenced by temperature. So ice cream depends on temperature. All right, so here is an example to take a look at. So we want to look at how much we spend on advertising and the sales. Okay, and so conceptually, hopefully, if we have a successful marketing campaign, if I spend more on advertising, I'll get more in sales. So my independent variable is my advertising budget. My dependent variable is sales. Hopefully, they go up together. If I increase spending, I'll increase my sales. And so here we can just look at the data set. And once again, I'm using the data.frame function. I'm assigning the arrow operation. I'm creating the sales data set. And for each column of data, I have a vector specifying what data values I want to see in there. All right, the next concept is population and sample. Population is what we want to know about. Sample is the data we actually have to work with to make an inference about the population. A population refers to the entire group of individuals, objects, or events that we're interested in. For example, the population of interest might be all students in a particular school. A sample is a subset of the population that we have the opportunity to look at, study, and analyze. The sample hopefully will be representative of the population so that the results of our analysis can be generalized to the population as a whole. So population is what we want to know about, but the majority of the time, we will never actually work with the population data. It's too large, it's unavailable. The sample data is the subset of data that I am able to get my hands on that I use to make an inference about the population. An example of this would be if I want to know the average height of American males, well, I can't go out and measure every single American male, right? That's not possible. So what I'm going to do, I'm going to get a subset of American males. I'm going to get their height, and I'm going to analyze the data and use my results to make a conclusion about the average height throughout the entire United States. So here is another example. So I'm going to create a data set, and we're going to call it population data. We're going to have age, gender, and income. All right, so we're going to simulate this. We're going to go through, and I'm going to pretend that there are 1,000 individuals that I'm interested in knowing something about. I'm going to, so I'm using the computer to generate numbers. I'm using a random number generator, and I'm going to kind of flesh out, give a hard example of what I'm doing for statistics. I'm going to create fake data. I'm going to say that we're going to pretend that this fake data is what I would like to know about, but I will, in real life, in this situation, I will never be able to get the true complete population data. What I'm going to do is I'm going to get the best subsample I can of the population data and analyze that, and hopefully my conclusions about the sample reflect what's going on in the overall population. All right, so I'm doing random number generation, so I'm going to set the seed. This makes it so I can repeat my results later down the road. Now here, I'm going to randomly pick the ages 18 to 65. In this particular function, each age is equally likely to be selected. We're going to take 1,000 ages, and then I'm going to be sampling with replacement. What this is doing is that, let's say I randomly pick 20 out of the number. Now, some sampling algorithms, 20 would never be able to be picked again. So sometimes we want 20 to be able to be picked again. So imagine I'm at a raffle and we're going for prizes. And the first way, you draw a raffle ticket, and after the person wins, they never get to win any more prizes. The second way that we could do it is that we draw a raffle ticket, the person gets their prize, and it goes back in to the hat to potentially win a second prize, or maybe a third, a fourth, potentially more, prizes for them. Those are two different sampling schemes. Here, we're saying I take the age, I put it back into the hat, shake it all up, pull it back out. When I say replace equals true, that's sampling with replacement when I put it back in. Now here, we're sampling gender, male and female. And so here, for this example, we're assuming we have binary genders. We want 1,000 of them because we are making 1,000 fake people. And then I'm going to randomly generate some income using the normal distribution. We're going to say that the average income is $50,000 and with a standard deviation of 10,000. All right, so this is the first 6 rows of my 1,000 rows of data. And so we can see this. Now this will go down for 1,000 rows. And now let's create a subset of the data. So this is the overall true correct data set that I would like to know about. In real life, it's not possible to get all the values. There's just too many, or it's not accessible. I'm going to go and observe a few, and I'm going to try and use that to make an inference about the population as a whole. And so here I'm going to create a sample of 100. I'm going to randomly pick some rows of the data set, 100 of them, and I'm going to sample them and take a look and work with it. Now here I'm doing replace equals false. So what this is saying is that if I select a row to be in my sample, it doesn't go in twice. So can't be in there twice, can't be in 3 times, 4 times, whatever. And so here, this is my first 6 rows of my sample data sets. So in this example, we created a pseudo data set of a population of 1,000 individuals, and we had age, gender, income. We used the sample function to generate a subset or select a subset of 100 observations. And one thing that is important about this is that replace equals false means that I never have the same observation twice in my sampling. That in real life scientific studies, I may or may not want to have replications, repeated observations. Depends on my situation. So each observation is selected at most once, and we selected the subsets by row numbers to achieve this. And we use the head function to look at the first 6 observations in both of those 2 data sets. Now, the next thing I want to talk about are descriptive and inferential statistics. Descriptive statistics describe the data. All right, so we're going to try and summarize our data, and organize things so it's easier for us to understand. We're going to summarize everything into an easier format for our audience to figure out. So we're going to use central tendency is the first one, the most important one for us. And what central tendency does is it just says, overall, where is my data along the number line? All right, so it's just location of my data in a one number summary along the number line. And typically we use the mean, median, and mode to achieve this. So the mean is just add them all up, divide by number of observations. The median, if I take all my data set and I put them in a line, where is the middle of the data set? Where's the middle, the median of it? And the mode is the most frequent observation. Usually we don't actually use this in numeric data. We use this for detecting problems with our data most frequently. And another thing we want to do is to measure the variability. All right, so the first thing I want to know about with my data is where is it along the number line? After I know where is it in a one number summary, I want a one number summary of how spread out my data is. So that way I can figure out, what is my minimum value, what's my maximum value. I want to understand this first. And so we've got the range, which is the maximum value minus the smallest value. We have the variance and standard deviations, and these are square roots and squares of each other. The variance corresponds to the second moment in physics. Inferential statistics is a branch of statistics that deals with making predictions or inferences about population based on the sample. And so this will include hypothesis testing, confidence intervals, and regression analysis. So let's build a data set, run through an example. And so I'm using set.seed to set it up so that I can reproduce my data set later down the road. When we use random number generation, I use the seed concept to be able to get the same data later down the road. And here I'm generating some normal random data. I have 100 observations with a population average of 50 and a standard deviation of 10. So let's calculate the measure of central tendency with the mean. And so here I'm using the mean function, and I just drop my data in. And so we can see that we got something close to 50. I generated data using 50 as the mean, and I got close to 50. You notice the sample is different than the population, and that will always be the case. Now, we can also calculate the standard deviation to calculate the spread. The population standard deviation is 10. My sample standard deviation is close, but not exactly 10, of 9.97. Now, hypothesis testing is the goal is to have an objective framework for reaching a conclusion, and we want that objective framework so that we are above reproach for anybody to say we're reaching an incorrect solution. We want a solid, mathematically coherent method of deciding on something. And so a question that might come up is after I have my data in my hand, I have my sample, a question that I might ask is the true average, population average, equal to 55? I have my data, and I want to know, is the true population average equal to 55? All right. Now, in this example, we know the true population average is equal to 50 because we generated it. But in real life, we don't know this. And so I have some idea of what might be reasonable, might be going on. I'll use hypothesis testing to evaluate it. So let's pretend that I don't know the population average. Let's say I have a data set, and maybe, possibly, the population average is equal to 55. All right, so what I'm going to do, I'm going to run a t-test to check my data versus the possibility that the population average is equal to 55. Now, I will never, ever 100% know for certain if it is equal to 55 or not, but I could say using statistics and probability I can measure, get an idea of how likely it is that the true average is equal to 55. All right, so the t-test is a tool that I'm going to use. Notice I'm dropping in the data. I'm saying that the population average is 55. Mu represents the population average in statistics. And so the p-value is very, very small. All right, so what this is saying is that if the true population average is equal to 55, then the likelihood that I would observe my data set is very, very small. Okay, and so if 55 is the correct true population average, and my data is very unlikely to be observed given that 55 is the true average, then there's probably something wrong. That population average of 55 and my data set together do not agree with each other. So something is wrong. Either my data is wrong or my hypothesis is wrong. Well, we take the point of view in statistics, our data is correct. If our data isn't correct, there's no point in running statistics and messing around with data. So you know what? I'm going to assume that my data is correct. And so the thing that has to be wrong is my hypothesis of population average equal to 55. And so I say, hey, my population average is not equal to 55. So we reject the null hypothesis that the mean of the data set is equal to 55 in favor of the alternative. This has a weird phrasing to it, and when we get to hypothesis testing, we'll talk about this more. So in this example, we first created a data set with 100 observations that was normally distributed with a true population mean of 50 and a standard deviation of 10. Then we use mean and standard deviation to calculate those values. And then we interpret what was going on. And then we use the t-test to evaluate the possibility that the true mean is equal to 55. And we rejected the null hypothesis in favor of the alternative, concluding that the true population mean does not equal 55. All right, so now hypothesis testing. Statistics does a lot of hypothesis testing. The goal here is to have a mathematically rigorous, objective structure for reaching a conclusion. So hypothesis testing is a statistical method used to determine whether a hypothesis about a population is true or false. Right? The process involves making a null hypothesis, which is the default hypothesis, and an alternative hypothesis, and we denote the null as h sub 0 and the alternative of h sub a, and then we'll test the null hypothesis using a significance level. Our significance level is our tolerance of a certain type of mistake we can make. We'll talk way more about this. The significance level is the likelihood of rejecting the null hypothesis when it's accurately true, and the significance level of 0.05 is commonly used in most situations. So let's create a data set. Once again, I'm using set.c to make my data set reproducible. So, in the future, if I do random number generation, I get exactly the same values. Here, I'm generating random normal data. Oh, and I copied and pasted this a second time. All right. That was a mistake on my part. All right, so here are some basic concepts and terminologies that's used in statistics. By understanding these concepts, we can begin to articulate our results when we analyze and interpret data, and this will help us make informed decisions. All right, so for your homework assignments, you're going to demonstrate your understanding of basic concepts and terminology in statistics by analyzing your own data set using R. So part 1, define qualitative and quantitative data, provide a brief description of your data set, and explain how it relates to your definition of qualitative and quantitative data, and create a summary table of your data set that includes at least one measure of central tendency and one measure of variability. For part 2, variables, we're going to define independent and dependent variables. You're going to identify at least one independent variable and one dependent variable in your data set, and then use R to plot the relationship between the independent and dependent variables. Then part 3 for population and sample, define population and sample. describe the population of interest in your data set. Use R to randomly select a sample from your data set. Provide a brief description of the sample data set. Then part 4, we're going to do something with descriptive and inferential statistics. So we'll describe descriptive and inferential statistics. We'll conduct a hypothesis test to determine if the mean of the dependent variable in your dataset is significantly different from a population mean of your choice. Pick a number that's reasonable. Interpret the results. Calculate and interpret a confidence interval for a population parameter of interest. You can use t.test to accomplish this. Now, when you submit, please submit an R Markdown document that is an HTML file. HTML files look really good in Canvas. All right, that's all I've got for you. Life is short. Do math.